So the motivation here is that I want to verify the logical content of proofs produced by real-world ITPs, and that includes not just the theorem provers themselves, but also sort of the libraries that have been built in them, and sort of what makes basically the content of our communal effort. Right? And when I say verify the logical content here, I really mean being able to make sense of what the actual proof is in some sense. What is the actual proof? What logic is it working in, and why should I believe it to be correct? Some of the ITPs are working towards what I'll call self-verification, and I'll explain what this means, but for now let me just sort of list some projects that have something akin to self-verification. Some of them have additional, so Coq has a project called Metamath, which is about verifying the Coq system itself. Lean has a project called Lean for Lean. Agda, well, there's some work going in that direction. Hausdorff has a paper on verification of the kernel in Hausdorff, and Metamath 0 is a system that I'll talk to you about more here. This is generally a really hard problem. A lot easier is to export to a simpler verified system. So the idea is that maybe your ITP is not on this list, or even if it is on this list, maybe one of these projects isn't done yet. And so rather than waiting for that project to finish, you can instead take your system and then export it into one of these. And so this gives you some kind of relative consistency proof. Sometimes it depends on exactly how you write this kind of export. And the export itself involves describing what is the logic of the source system in the target language. And so that can actually help to give outsiders some view into what all is going on in this system. Right? One of the things that I want to emphasize here, though, is that the export actually has to be practical. I showed you this list of big projects, and if I can't check these projects after doing the export, then it's not that useful as an export. So I really want this export to at least be practical enough. Sometimes that means you might have to write more exports to avoid, transitive blowups, but I'll get to that. So yeah, practical exports between all of the systems in common use and systems that have some kind of self-verification or mutual self-verification. Question?
There's just a comment or maybe a warning. So in my experience, you won't be able to have a simpler export to a simpler system. It's like the simpler you make the target system, the more complicated your export gets.
That's right. But I mean, the export itself describes the semantics of the complex system. So that's sort of to be expected. That's, I would say, okay. At least you're writing down in some declarative fashion what it is that the complex system is supposed to be doing. And that's the sense in which this sort of gives meaning to the goings-on of the other system, let's say. And so this is a way of sort of communally bringing meaning to these systems. So, of course, the natural question is, well, okay, but export to what, right? I would argue actually that it doesn't matter that much because these exporters are actually easily retargetable. An exporter sort of encodes the information about the kernel language and the primitive inferences of the source system. And this is true even if the source doesn't even have a kernel, right? Writing the exporter sort of gives you a kernel, like that's kind of what it's doing. But if we're asking the question, then I do have a suggestion, and I'll tell you about that. So now you've all seen a picture like this before. People draw a bunch of things around the side, and they put, who knows what's going to go here in the center. And then they'll say, oh yes, everyone brings your things to me, right? I think that this is just the wrong idea, right? Instead, we want some kind of more web-like picture where different systems are exporting from and to different things. Ideally, this graph should be connected, and ideally, it should also have the property that every node connects to something that's involved in a cycle. These cycles basically represent these self-verification or mutual self-verification tasks, and this would allow you to take a proof done in any system, transport it along some number of translations, and then get it to something where within the language itself it has some sort of semantics. And then you can basically pick any of these sort of root nodes as your kernel of truth, right? The thing that you personally believe in. If you've studied any of these systems, then maybe you'll have one that you're most familiar with, and then this will allow you to look at the stuff that some other guy has done, and then pull it into your system and say, oh, I understand it now because it's written in a language that I know. So again, the end goal here is that every system is either self-verified or mutually verified, or is translated to a system that is. And moreover, these translations have to be efficient enough to actually send full libraries across them. And then as a result, we end up with more confidence that the proofs are not exploiting some weird corner case bugs in the checkers, because an exporter will generally have trouble translating a proof that was done with a checker that has a bug in it. And then we also sort of get a formal specification for the proof languages of all of the systems involved. Okay, so I'm gonna give you some, question?
Can you, if you compose two translations, can you kind of eliminate the intermediate language?
Yes.
Do you expect it?
Yes, that's the idea. So, you don't have to stop, you can translate from here to here to here to here, right? And, you end up with this embedded inside this. And ideally, you should try to set this up so that it doesn't end up within 4 layers of onion rings, but yes, this can absolutely be done.
So Mario, you seem to be quite concerned about actual correctness and trust.
It's easy to phrase it in those terms, but in the same way that formal methods isn't really about correctness, I think this is not really about correctness either. Okay. But that's sort of the obvious thing that you can cash out of this, but I think that the more interesting thing is more the being able to describe the semantics of the source system in some declarative language.
Because you mentioned it a couple of times already.
Yeah.
Okay, then I'll shut up.
All right, so I'm going to tell you sort of a little story here in order to motivate why we should trust a proof checker, and in some sense tell you a little bit about self-verification. I'm going to start with sort of proof as a social process, and here I'm not even thinking about computers. I'm just thinking about how does one person tell another person a proof, and so Penny here is a mathematician. They've just proved some big thing T, and they want to share their work with the world. Victor is a professor who is interested in Penny's work, and they would like to be convinced of the truth of the statement T. This is a pretty normal situation in mathematics. The usual process is that Penny will write a document in plain English, going through the logic of the proof, leading readers, in particular Victor, to have no choice but to accept the truth of T. And then Victor reads the proof, checks that each step contains no logical errors, and thereby is convinced that T is true. This is sort of how we like to think of mathematics as happening. This is, of course, an idealization. Other ways that this could play out might be that Victor decides that T is just too unlikely to be true, and Penny couldn't possibly have proved it, and so Victor ignores the proof. Right? This is the sort of crank that proves Riemann's hypothesis or something, and then you see this and you're like, no. Another sort of the converse error is that Victor decides that Penny is trustworthy and does not read the proof very carefully, and is convinced of T, despite the fact that the proof was not in fact read. This is the sort of Schultz's worry about no one's actually reading my proofs. I need to know, how do I verify these things for myself, because the reviewers are not helping me as much as I would like. So how can computers be used to facilitate this process? So there's basically 2 ways. Penny could use computers to feasibly build larger proofs, and then Victor could use computers to feasibly check larger proofs. Now, 1 is definitely true, but 2, it's less clear how we can do this. If Penny has a very large proof, then the communication process can break down. If Penny starts sending thousands and thousands of pages of plain English, it might start becoming a problem for Victor to just read all of that text. So how can Penny, knowing that this is going to be a problem, lift the burden on Victor and address this imbalance? So I'm going to introduce RoboVictor. Now, RoboVictor is just like Victor, but he's a robot. He can read proofs carefully and ensure that there are no flaws in the proof. He never gets tired, and he can work much faster than Victor. It looks good, but RoboVictor is not Victor. Victor can watch RoboVictor be convinced without themselves being convinced. So we need a new strategy. Penny writes a document in RoboVictor's language, going through the logic of the proof, leading RoboVictor to have no choice but to accept the truth of T. Penny convinces Victor that RoboVictor is a valid proof checker. Victor reads the statement that was written in RoboVictor's language that determines what RoboVictor checked, and determines that this is in fact a way to write T. Now, one thing that I want to observe here is that in step 2, this statement here that RoboVictor is a valid proof checker, it's not specific to this proof that Penny was doing. And so maybe we don't actually need Penny to do this job. Instead, maybe we'll have, Mario the meta prover who convinces Victor that RoboVictor is a valid proof checker. So, okay, so now we have a new strategy. So Penny writes this document. Mario convinces Victor that RoboVictor is a valid proof checker. And again, Victor reads the statement. Now, Victor has 2 jobs now. One is to read the statement, and one is to be convinced here in step 2. But it's still a lot less work than the original plan, because actually the big proof part, the thousands of pages, that's all in step 1. So in some sense, the hard part is now being done by RoboVictor. And again, the observation is that step 2 here is a mathematical statement that some particular computer program checks proofs according to some rules. So it sort of fits within the same scheme as what I've been showing. So this leads us to the idea of bootstrapping. So for those who don't know, bootstrapping refers to the idea of picking oneself up by the bootstraps, the sort of image of like lifting oneself up by just picking yourself up by your bootstraps. It's a self-referential foundation. So now we're going to play this whole thing where we prove step 2 using the same scheme as the full 3-step process. So now Mario is writing a document in RoboVictor's language, going through the logic of the proof, leading RoboVictor to accept that RoboVictor is a valid proof checker. And then Mario convinces Victor that RoboVictor is a valid proof checker. And then Victor reads the statement and determines that this is in fact a way to write this statement. And thereby Victor is convinced that RoboVictor is a valid proof checker. Now you might notice the problem here. This is a circular argument because step 2 has not changed. It's actually the same as what it was before. So we actually need one more version of this. It's document in plain English going through the logic proof. This is in fact the same as our first version of the proof before we'd added the computers. So we have some plain English reason to believe this statement. And then Victor reads the proof and is convinced that it has no logical errors, and thereby is convinced of this truth. So essentially what this is you have a self-referential proof, and then you also have a sort of plain English proof, and the self-reference actually helps with being able to trust this proof more than you would if it was just on its own. So it doesn't sort of stand on its own, but it is a bolstering mechanism for other methods of proof. And this is why sort of self-referential proofs are not completely useless, right? Like if you think about them as a sort of pure syntactic artifact, it just looks like nonsense. However, there is a sort of way in which they can be used to improve support that you already have by other means. Okay, so the Metamath 0 project is basically trying to solve this problem of constructing this so-called RoboVictor. Metamath 0 specifically is a specification language which allows you to write pure statements, and the analog RoboVictor is the MM0 verifier. And just to give you sort of some overview, there's basically 3 components in this architecture. The first one is MM0 itself. It's the logic and specification language. It has a symbol structure, standalone verifier, sort of a small trusted kernel. The second component is Metamath 1. This is a proof assistant that produces Metamath 0 proofs. This runs tactics, metaprograms, and it exports Metamath 0 proofs. And then MMC, or Metamath C, is a proof-producing compiler. This is a programming language for producing programs with a proof of correctness. I'm not going to describe this, but I can talk to you more about it if you're interested in verified programming. Yeah, so we use MM1 to write proofs in the MM0 logic. We use MM1 as a framework to run the MMC compiler, and then the MMC compiler produces MM0 proofs, and the MM0 verifier is written in Metamath C. So the idea is that this is a framework for, like, how would you approach the problem of constructing a verifier that is compiled down to x86 and has a theorem proved about it that says that this thing is a checker for the language that it is compiling. Okay. So just to make this less sort of philosophical and give you some actual code to look at, this is just sort of what a simple MM0 file looks like. So this is defining propositional logic. And I mean, I'm not going to define the details here, but it's fairly straightforward and sort of LF-ish. You have term constructors, you have axiom definitions, and then here's a theorem. And you might notice that the theorem actually doesn't have a proof after it. This is basically a long elaborated theorem statement. So you think of this as, here's a bunch of axioms, and then I claim that this follows. And then there's a completely separate file that provides the sort of evidence that this is true. And then sort of continuing on, we can write down piano arithmetic. So we have a sort of natural numbers, we have zeroth successor, we have some axioms about successors and the induction axiom. And then addition and multiplication, addition and multiplication, evaluating on successors. And so, 3 pages, we get piano arithmetic axiomatization. That was a complete axiomatization just given. And it's quite expressive. You can define all of these things in piano arithmetic, and we do. And this is used for the proof of some properties of x86 and so on.
Your back one was like, okay, wait. Right, okay. I was going to ask, how do you know that plus is plus, and now I see.
Yes. Yeah, so I
plus.
have,
Okay.
yeah. Mm-hmm. Good. Okay, any other questions? Okay. So I'm not actually going to talk about Metamath 0 all that much, but this is just to give you some vague sense of what it's about. And now I want to tell you about sort of the meta project that I've been working on for quite some time, which is basically a bunch of little projects of exporting between different systems. So I go into a system, find out what's the state of the exports, and maybe improve it. So, Raleen, what is the status of exports? Well, so one of the things that, and I should mention that this is very much biased towards my own work. So, if you know about additional work that is not on this slide, I am very interested to hear about it and possibly use it. There's a file lean.mm1 which defines lean's theory axiomatically, and this would sort of be the export target. However, there is no current lean2 mm0 exporter. The plan here is to adapt an external lean verifier to generate typing proofs. And lean for lean has a specification of lean's type theory plus a verifier. So this is sort of half of the job. The other half is making this thing proof producing. And there's also another external verifier called Nanoda by Chris Bailey, written in Rust. My understanding is that there is possibly a lean to deducti translator. I'll get back to the deducti translations. On the import side, however, there is a working translation from Metamath 0 to lean, and I have actually used that to transfer theorems from the Metamath library in lean, so that's good. In Coq, on the export side, well, Metacook is still sort of trying to figure out what the language is. I have the very beginnings of like what might be a kernel eventually. There's something in Coq to deducti. But again, I'm not exactly sure on how complete this is. There is this result about translating lean into Coq. Although it doesn't, you have to sort of turn off some flags, make some things slightly unsound in order to get it to sort of fit.
So you can slightly prove false?
you can slightly prove false. So yeah, it would be nice to have something better. Okay.
Claudio has an exporter that is not on the list, I think.
From
From Coq to some XML in between.
that might be the
Jason.
cockpit deduct.
No?
No, it's a different one. Do
It
you know what
might
it's
be.
targeting?
Hmm?
Do you know what it's targeting?
What?
Or it's just cockpit.
Which translator?
It's some kind of cockpit based on.
Claudio Zattidotico and that we've used in OAF. So he's
Okay.
over there, so we need to talk to him.
Okay, yeah. So yes.
Just produce ad hoc XML.
What was that?
Just produce ad hoc XML representation of Coq.
I see. Okay.
Although it might be that it does not contain the proofs and only the statements.
Yeah. This is I'm definitely focusing here on sort of the full proof producing together with the cement. Like you can actually run a type checker over it and verify the full content of the proofs. And so that does exclude some.
Remembering it, but I thought he said that was a lambda pi, which is kind of deductive, kind of. Right?
Yeah. Lambda pi is basically deductive.
Deductive, right?
Yeah. Okay, so yeah, possibly a second. Maybe there's two cognitive deductive things that I should put here. Okay. So in Isabel, so that for export, Stefan Berkhofer wrote this proofterm.ml, which exports lambda terms from the kernel inferences. However, it is too inefficient to check the whole standard library, let alone the whole AFP. And Makaris has been showing me this zterm.ml thing, which promises to be more efficient. I tried to run it to export hull, and I ran out of memory. So I'm still hoping that there's
Work in progress.
work in progress. Okay, so all right. Well, I'll love to improve the status of this in the work group, possibly. And yeah, I managed to write a parser though that can read that data. So if I ever manage to get that database, then I'll be able to read it. It's not yet occurring. So there's I believe that some aspect of this this pipeline is being also used for deduct export. And on the import side, I'm familiar with one work that was making Hull 4 run inside Isabel. I'm not sure how many other languages have been used for translation to Isabel, but that's one I'm aware of. In Mizar, I wrote an external proof checker for Mizar last year, and I've been working on proof term export from it. And so I hope to get the Mizar mathematical library in some kind of externally checkable form from that. And so that will be very useful because otherwise I'm not sure what will happen to all of that great work. In Metamath, this is sort of the only one on the list which I can actually say, yes, there is export, yes, it works. Metamath can be translated to MM0, and MM0 has been translated to other languages, so I have full pipelines involving the Metamath stuff. Set.mm is about 30,000 proofs, so it's comparable in size to some of those other big libraries that was mentioned in Fabian's talk. But it can be used to translate that language into MM0, so you can test MM0 at large scale, which is useful. And I use this for a proof of concept translation of Dirichlet's theorem. There isn't much in the way of imports. Hullite, there's a translator to Common Hull. Unfortunately, this translator is closed source, and I haven't heard much from the guy who's doing this in some time. There's also translation to Open Theory, and again, I haven't heard much from the guy doing this. Hullite has a self-verification paper some time ago. I wrote a Common Hull verifier that can check fly spec. So the Mark Adams. So Mark Adams wrote this Common Hull export, and he also created the Common Hull exports for the FlySpec project, and so I can read those and translate those. But unfortunately, Hullite itself is sort of a programming language kind of. You have to trace the kernel and do some stuff in order to get stuff out. So maybe I'll do that later. But yeah. Metamath 0, this is just sort of a summary of previous slides because I've already stuck them there, but There's import from Metamath, and there's export from M0 to sort of a generic hull, and then that sort of is used as the basis for these two translations into open theory and lean. I'm pretty sure I can stick Isabelle in here as well, although Isabelle's proof term input format is non-existent. I don't know exactly what that would look like. And Deducti. So Deducti is doing very great on this. I mean, this is basically the purpose of Deducti as a language, so it's good to see that there are so many imports. They're not doing so well on exports. It's a little bit funny, right? Like, I mean, in some sense, Deducti is doing the drawing from the beginning, where you have all the guys going into the blob in the center, which is Deducti. But I also want to make sure that this graph has sort of all, that everyone has an out edge, right? And so there is so these exports and imports were based on just looking at all of the repos on Deducteam, but I don't know what state any of these are in. I think most of these are somewhat partial. I don't know whether you can tell me whether any of those are like definitely complete.
I think so. Open Theory and All Light are complete. I mean, they can translate everything, I guess. And for the other systems, then it's not total. For Isabelle, in theory, we could be able to translate everything, but then, I mean, the export from Isabelle is too slow.
Yeah, so so a lot of these are not complete, but it sounds like some of them are, which is good. And also a lot of them have difficulty with scalability. Although I'm not sure how many of these are, these are probably not Deducti's fault. This is more the fault of the exporter itself. A lot of them, like the Isabelle exporter is already sort of having trouble in the first stage of the export, even before it gets to a target. Do you have more to add?
Yeah, so actually it's possible from Deducti to go to Open Theory, PVS, Coq, Matita, and Lean 3, I guess.
But these are partial exports, right?
No, it works, and for theorems that are in higher order logic, the encoding of higher order logic. So you can export this, and there has been some experiments. So for instance, the Matita library of arithmetic has been translated to all the other systems.
So you can take Matita and put it into PVS or something like that?
Yeah, it has been done. I mean, it's available on the web.
Okay. Excellent. For the other sort of theorem proofs I haven't listed so far, I have thoughts about how to do exporters for several of these other systems. And then if your system still hasn't been listed, then I'm very interested in knowing more about it and writing some kind of export from it. So here, just to give you some, some small pitch for why should you use Metamath 0 specifically as a proof interchange language. So it's sort of designed, it was designed as a verifier for the self-verification purposes, but it was also sort of really focused on this sort of back-end stuff. And so I like to think of it as a sort of assembly language for proofs. This sort of gives you a sense of like, it's something that is really well optimized for like compiler pipelines, right? Like if you have some nice front-end syntax that gets turned down into some core language, and this is the core language that can be checked really efficiently. And this thing, competes with IO-bound routines for like its verification, right? So there's really, it's very, very easy to check, and it's also quite expressive. So you can, you can write higher order things and so on. And so there's some stuff about the thing uses some stack machine representation of how to do the proof checking, and this can be proved to have some nice linear time checking properties. And it's also very parallelizable. It's sort of annoying that I don't actually have any databases that are large enough to stress this tool. It is too fast for all the things that I give to it. So I really do want to get all of those big libraries so that I can test this tool on them.
But
because Metamath is not big enough.
you do have FlySpec, right? Like you
I do have FlySpec, yes.
And those numbers, they were over 1 minute.
Yeah, it's like 10 minutes, I think.
Yeah.
So, I mean, we're getting there. But, huh?
What counts as a stress test for you? I mean, there are like 20,000 graphs you could check, but they're not Hamiltonian.
I mean, so as I said at the beginning, my goal is really to track the sort of the pure math libraries of ITP systems. There are there's lots of interesting mathematical content to be found in these systems, and I want that to be checked in a reasonable time frame.
So you said FlySpec was 10 minutes?
Yes, I believe it's in that range. Well, so that's this is 1/3 of FlySpec. So FlySpec has basically 3 components. One of them is sort of the paper-proof part, and then there are 2 parts that are somewhat computational. One part is sort of half step is an Isabelle. So it's actually quite a complicated, checking procedure. But here I'm talking about the paper-proof part of it. That was the part that was translated into Common Hall.
Okay, so that takes 10 minutes on your laptop.
Yes.
How long does Mathlib take to compile on your laptop?
I haven't tried in some time. It's probably in the range of an hour.
This is different. Like he's checking the proof trace, not the proof search. That is.
Oh yeah, that's also true. So checking Metamath proof terms, I think is half an hour, something like that. Maybe in that range. Like if you're running lean, lean for lean or something like that, it's in the range of half an hour. So the idea is that you should be able to do this part of the process in less than half an hour. Usually that half an hour is spent on the proof export process. So basically, when you stick a proof exporter on, it acts like a proof checker for the purposes of its general runtime. And then the Metamath 0 checker part that goes after the end of that ends up usually being much faster than all of the previous steps of the pipeline.
Sure.
And so, yeah, it's just...
So you say you want to stress this, I'm just
Yeah.
trying to get a gauge of what the reference times are.
Yeah. So half an hour would, I'm feeling good about that, taking a reasonable amount of time. When it's like 1 second, that's not a stress test, right? Okay, so just to recap, so the shortest path to make sure that the ITPs of the world have a well-defined semantics is to export from everything to something, okay? And the limiting factor here is really domain expertise to build the tool, the exporter, and buy-in from the community to keep it from rotting. This is actually also really important. Like the open theory tool, it is built and it works for a while, and then the libraries move on and no one's paying attention to it, and so of course it sort of falls over, right? So, you have to start by building it, and then you have to get people to use it enough to keep it from dying. And yeah, so I have some program that is fast enough to not be the limiting factor in this pipeline, and it's intended for self-verification. But I really want to emphasize this is not a competition between these systems that are doing exports or whatever. This is a cross-community effort to connect every theorem prover together. Every edge in the translation graph helps here. So thank you.